Good evening, everybody. I'm going to go through the practicalities of the welding. It's touched on some of what I've done, but it introduces some of the bits about the tenacious oxide layer on there, which is not brilliant for welding, so you have to get rid of that. So I'll run through it. That's a typical butt weld with aluminium, just to introduce it. MIG is the most commonly used process for welding aluminium throughout the country. When welding aluminium, its absolute cleanliness is essential about the tenacious oxide layer, and any sections above something like 10 millimetre, it's probably a good idea because of the high thermal conductivity of aluminium to preheat it. Otherwise the heat will just dissipate from the weld area and you'll struggle to get a good weld from it. So when welding aluminium, it's totally inert shielding gas. This must be used. So it's either pure aluminium or aluminium argon mixtures with helium are standard for us, but nothing with an oxygen or a CO2 content, as they will ruin the weld. Aluminium wires are very soft and tend to buckle when being fed. So to minimise this effect, special liners, Teflon liners, need to be used. And generally speaking, the torch length is about 2 metres or 3 metres, but certainly nothing at 5 or 6 metres length, because pushing it down that sort of length on a small wire, diameter wire, with aluminium being soft, it will tend to buckle in the liner. So sometimes push-pull guns are used for this application. So you're pulling it from the torch end or the welder's end from the wire feeder, and they work in conjunction with each other. The other main problems accounted when MIG welding are the porosity and solidification cracking in sensitive alloys. Attention to joint design and cleanliness using the preheat. Correct fillers, current and heat input are vital for the problems to overcome. So it's very difficult to weld. Mild steel's quite easy, stainless steel's quite easy, but of the common ones, aluminium's that's that little bit more difficult to weld up. Standard MIG alloy equipment is suitable for welding alloys, so it's a standard welding machine in general. It can be used for it. You're capable of doing it. Some of the more sophisticated ones are much better for welding aluminium, but a standard welding machine, provided you've got that shorter torch. Water cooling guns are recommended because of the high heat input from the torch and the current you're using. It's necessary to ensure that soft wire rollers, so you don't use a standard roller, they will damage the wire, and then that will cause a problem of feeding through the torch liner. Aluminium soft wire has a tendency to fold or buckle, and when being pushed through the feed rollers and the conduit in the MIG gun, to overcome this problem, a push-pull system or spool-on gun is used. Consumables normally chosen to match the base material, not that far away from it, they tend to be matching. Competitions are as close as possible to the aluminium alloys to put into practice. However, with structural steel aluminiums, it is not always possible to choose that filler wire, so different filler wires are there. There is a table available from the AWD, the AWS, what is a American Welding Society, and they tell you what to use for joining specific materials, or when you're joining dissimilar aluminiums, it will tell you the right correct filler for that. That's a brief one that goes through the more popular ones, but there is a wider table available. So the choice of filler metal depends on the required weld seam properties. Depending on the application, the required properties can be varying. Shielding gases, which is where we come into it. MIG welding of aluminium and alloys is totally inert. Shielding gases must be used, and active components such as oxygen, generally used in mild steel and some stainless steels, carbon dioxide present in minute will cause oxidation and will prevent the satisfactory weld being produced. In the practical terms, the choice of shielding gas is limited to argon and helium, or a mixture of both. While pure argon is widely used, there've been more recently towards the argon-helium mixtures because they give a hotter weld, and that's what you're trying to achieve. The helium gives you that much more heat. And it's, our trade name for that is AluShield. We have three types of AluShield. One is for thin material, which is AluShield Light. AluShield Universal for medium thicknesses, and for heavy sections we call heavy. We have it called AluShield Heavy. So a lot of that. AluShield is a trade name for our products, as I've just said, and then we go through the different grades. So AluShield Light, which is the thinner of the materials, we only have a 30% helium in there, and up to the Universal with 50 or 75% helium, and the heavier sections, more helium, more heat is makes the weld more fluid. And then as I said before, then it's a preheat is generally required on anything up to 10 millimetres, which is where you would use the AluShield Heavy. That gives an impression of the effect of adding helium. Same thickness of material, same consumable, same parameters, but adding the helium in it, as you can see, gives you better penetration characteristics. And with the argon, it's minimal, and you might struggle on certain thicker sections to achieve a full strength weld across the section of the material. Obviously, the effect of the extra heat is that you can actually travel at a greater speed, and instead of it's double the speed of a normal weld, normal welding with argon, as opposed to using your AluShield Heavy. Practical considerations: many aluminium alloys are susceptible to solidification cracking or liquid cracking, and some are virtually unweldable. So we went through some of that before. Some of the other guys had told you about some grades of aluminium are just not weldable at all. When this is established, a filler wire with sufficient alloy content produce a sound crack-filled weld can be chosen, checking that the aluminium wire choice is compatible with the aluminium being welded. Sections over 12 mil or under certain surfaces thinner material, it may be necessary to preheat. Preheat is applied to aluminium for two main reasons: to drive off the surface moisture due to either condensation or absorption into the surface of oxide film, which would otherwise break down into the welding arc to produce hydrogen and result in porosity, which is another problem with aluminium. When welding aluminium is porosity. It's always there. It's in minimal amounts sometimes if you get it right, but it can be quite extensive. To counter these effects of thermal conductivity, heat away from the weld area, it's ensured good fusion can be achieved and start the weld using shielding gases containing helium. As I said, that gives you that. It's recommended only oxyacetylene is used when preheating aluminium, because propane gives off a moisture, and you're adding moisture back into the weld again, which is what you're trying to avoid. Acetylene doesn't have that property. Cleaning. I think we've been through that already about getting off that tenacious oxide layer there. Generally, it's done immediately prior to welding, within sort of 5 minutes of welding or less, if possible. Generally speaking, with welding, it's carried out by using a stainless steel wire brush, and sometimes some chemicals. It used to be acetone. I'm not sure you're allowed to use that anymore. Is that? That's no. But, anything that can clean it better than it. But generally speaking, either that or Scotch Brite. abrasives to clean that surface off. Once you remove that oxide layer, it's a lot easier to weld, and it's a lot easier to get a clean weld pull. Solubility of hydrogen in molten aluminium is much greater than it's in solid aluminium. Thus, liquid welding metal solidifies. Hydrogen will be forced out and result in porosity, which is not something you're not trying to achieve at all. Obviously, that has an effect on the strength of the material and the weld as well. High thermal conductivity aluminium means that the weld pull freezes quickly and reduces the chances of entrapped gas escaping. Porosity tends to become more of an issue in thicknesses, in the thickness of the material being welded increases, since the gas has less distance to travel to escape, so it's all being entrapped in there as the weld metal is solidifying. The main causes of porosity in aluminium: inadequate cleaning, allowing the moisture to or hydrocarbons contaminate the remain in the plate or on the weld surface. These are contaminated releases hydrogen into the weld pool during welding. Too high or too low gas flow rates is important. If the flow is incorrectly, it can train or the atmosphere into the weld surface, or causing by turbulence. Use of pure argon shielding gaskets can exacerbate the situation due to its relatively low energy input into the weld, so it hasn't got the same heat properties as a helium-based gas. And combined with the high thermal conductivity of weld leads to a fast freezing pull, entrapping the gas again. This is especially significant in materials above 10 millimetre. Porosity: to avoid or minimise porosity, the following actions are recommended. Make sure the material is thoroughly clean before welding. Make sure the MIG wire is clean as well. No oil on there or anything like that. Generally, they come quite clean from the suppliers, but if it's been sitting around in a workshop, picked up and used for a second time, then you've got to make sure it's been wrapped up in a polythene bag or something. Make sure the wire feed equipment and components of the wire feed are clean, so obviously the equipment you're using is not picking up contaminants from there. Use helium mixtures such as Alice Shield and put more energy into the weld area, slowing down the time it takes to freeze, the weld pool to freeze. If using pure shielding gas, you may have to preheat the material. Make sure the correct shielding gases flow rates are used, and for more welding applications, a flow rate of between 15 litres and 20 litres per minute is adequate. It's all important to check that the flow gas at the gun, it's not using the flow gauge on the wall. It's best to use it at the end of the torch, and that's where you get the most correct reading. There could be constrictions in the torch and things like that make it less at the torch end. So it's the torch end is the important point, and 18 to 20 with a helium-based gas, it's much higher than it would be for welding mild steel. So there's two types of cracking. I won't go into great detail. It's liquefaction cracking and solidification cracking, and both of those are dependent on the material being used. So it's worse if the wrong material's been used. Also, quite important is the weld preparation. Square edge butt doesn't tend to work very well with aluminium, so you put a preparation on the bottom side, or the other side of it, the penetration side of it, and you get a much better root formation, which is more acceptable, rather than on the left-hand side where you've got a suck back and it's not deemed to be a good aesthetic weld. The other side of it is TIG welding, or GMAW welding of aluminium. These tend to be much high quality welds, but it's much slower process, probably more suited to thinner materials. thinner sections of aluminium, particularly sections up to about 6 millimetre. After that, it becomes very difficult, or very the size of the currents you're using and the size of the electrode becomes difficult to weld. TIG welding of aluminium can be carried out using 3 standard types of operation moves depending on the current: AC, direct current, DC negative, and electrode positive. AC is the most commonly or most frequently used for removing that oxide film. It's the electrode positive cycle, and the heating occurs in the electrode negative cycle. So alternating current breaks that oxide layer down, as well as the cleaning effect that you've already produced to it. So both TIG and MIG, you need to clean it before any operation of welding.